for you guys? Great. So I'll be talking today about some joint work with Seth Neal, Aaron Roth, Bo Wagner, and Stephen Wu, all of whom were at Penn at the time. Stephen's now moved to a postdoc at Microsoft Research. And basically the backstory here, the justification for this work is that many of today's most interesting computations are on individuals' personal data. And I mean, we see this, in the question of sort of how does Facebook decide what to show you? How does Google steer your attention when they get the opportunity? How are the ads that you're shown when you're online get chosen? How do you get driving directions, movie recommendations? And then even sort of more important decisions, like how is it decided whether you get a loan? How do we decide if new medications and new medical treatments work? There's so much that's going on in this rich space of personal data. And many times, sure. And many times, we might be interested for a variety of reasons in.
Katrina, is your mic off by any chance, or it simply doesn't work?
It says it is on.
This is just recording. I see. This is only recording.
Okay.
It's not,
If my volume's not good, though, let me know. And maybe I will shut the door. So many times we wish to do these computations in some way that protects individual privacy. And we might want to do this because of legal or regulatory requirements. We might do this if we're a company like Google because we actually don't want our hands on data that we don't need, because it's going to get us in trouble later on. Some subpoena is going to come, or there's going to be some other situation. And some of that is the legal side of it. Some of it is the public perception. And in many cases, there are large companies that have taken some efforts to make themselves sort of known as being on the side of the consumer. They're pro-privacy. This is part of the brand identity. And this is something I think you see with Apple and their adoption of differential privacy. So, like I said, sometimes the privacy requirements are clear and binding. So there's sometimes when you really actually have to protect individuals' privacy. But in some of these other situations, you're providing privacy as a convenience or as part of a show that you're putting on. And it's not necessarily the first order concern. So in a lot of these other situations, it's a little bit more complicated. When you have to provide privacy and there's a particular level of privacy that you need to provide, then we have a pretty well-studied optimization problem. There's a whole sort of literature on differential privacy that goes around saying, if you need to provide a particular level of privacy to individuals, what is the impact on the accuracy of the computation? This is a pretty well-understood question overall. And this is how it gets phrased. You have a privacy requirement, and you want to minimally impact accuracy. But when we're in these other situations, and the privacy requirement is not necessarily clear or binding, but it's sort of a secondary concern, then what the literature has to say is actually much more limited. And so what I'm going to be talking about today is sort of this privacy question coming from the other side. What if it is the accuracy constraint that is the binding constraint? You need to achieve a particular level of accuracy, and the question is, given that constraint, how privately can you do your computation? What is the best privacy that you can offer? And so in order to address this question today, what we'll be doing is, first I'll briefly give you sort of the formal framework in which this work operates, which is differential privacy, and give you a little bit of the background fairly quickly that you need for that. Then I'll talk about the problem that we're trying to address, the learning scenario in which we want to achieve privacy as best we can, given a particular accuracy objective. And then at the end, I'll give you some hints about the technical components that go into that, and some evidence that maybe this is a promising direction. So first, privacy. I've been talking about privacy. What do I mean by privacy? Probably most people in the room have encountered differential privacy in one way or another, but just in case not, let's go to it. So informally, the promise of differential privacy is that access to the output of your computation doesn't let anybody learn much more about anybody than they might have been able to learn had you done the same analysis without that person in the database. So sort of thinking about another way, if you have a computation and that computation has some true underlying answer, you're going to randomize and somehow intuitively add some noise to your computation so that you induce some distribution over the outcome space that's reasonably concentrated around the correct answer. And what you're going to promise in doing so is to each individual who might have participated in that computation, you're going to promise them that if they were to leave the database, that no outcome would change probability by very much. So basically, intuitively, you're saying, don't worry, you might as well participate in our computation. So let's make this formal. So differential privacy operates in the statistical database model, where we have some set of possible entries or rows. Think of this as one row per person in our database. We can use a running example of, say, a database of people's medical information. So a row might contain things like my date of birth, some tests that have been run on me, some diagnoses I've received, all of the data that pertains to me. And we think of a database as a collection of such rows. We sometimes use a histogram representation where we just write out explicitly the number of rows of each type that we have in our database. And from the perspective of an analyst, usually the way that we tell the story is that she has some computation that she wishes to perform in the database. And we interpret computation fairly broadly. Maybe she wants to fit a model, compute a statistic. Maybe she wants to somehow sanitize the data that she has at hand. But that usually when we pose this problem, we have some hard privacy constraints. She wants to preserve the privacy of the individuals. And so she's going to somehow design her algorithm subject to a privacy constraint so that it's going to mask small changes in the underlying database. And it's going to behave approximately the same regardless of whether any one of us actually shows up in the database. So what does it mean to mask small changes or to talk about neighboring databases? So what we're going to do intuitively is we're going to require that our algorithm behave almost exactly the same on neighboring databases that just differ by the addition or removal of a single row. And so this is then the basis for the definition of differential privacy, which is just that our algorithm, for every pair of neighboring data sets and for every outcome that we might be interested in, or subset of the outcome space we might be interested in, it needs to induce almost exactly the same probability mass on that outcome under the one database with me in it versus the other database without me. Okay? So this is the notion of privacy that we're going to be working with here. There's, at this point, a fairly substantial literature built up, basically over and over answering the question, if this is the question you want to answer on your data, if this is the computation you want to do on your data, how well can you do it subject to a privacy constraint of this form? Okay? And we have this whole literature now that really helps us understand for a broad variety of things that you might want to do with data, how well can you do it? How much does imposing a privacy constraint harm the accuracy? And so if you haven't seen these things before, this e to the epsilon, just think of this as a small multiplicative factor. So we're basically saying that the probability mass that lies on any outcome or any subset of the outcome space needs to be multiplicatively about the same under any two neighboring databases. So again, just for those who haven't seen this before, let's build up the intuition a little bit more. So basically what we're saying is if we have a database and we have some algorithm that we're claiming preserves some epsilon parameterized differential privacy guarantee, then what that means is if under a particular input database our algorithm induces a particular distribution over the outcome space, that if we were to change the database slightly, our algorithm would be forced. Your hands get tied, and you have to induce a very, very similar distribution over the outcome space. And this is going to be true for all neighboring databases. So you can see, sort of as you commit to the first distribution, the space of things that you can do on the neighboring databases becomes further and further constrained. Intuitively, another way to look at this is to think from the perspective of an individual who might be trying to decide whether or not to provide her data to a differentially private computation. So you're sitting there and thinking, I want to help science and all, but I'm concerned about some potential consequences of this computation. Maybe it's a computation that's going to be based on some of your medical data, and you're concerned maybe for yourself about the impact on your life insurance premiums. Maybe you're concerned for your descendants, that maybe someday in the future people will discriminate against them because of something that comes out in this study as a result of your contributing your DNA, your medical information, what have you. And what differential privacy says to you is, if you really can believe that the computation that's going to be done on your data gives this formal guarantee of differential privacy, and as an individual you think about, here are some possible bad outcomes that I'm concerned about. So you think of these outcomes of the algorithm, they also sort of induce future paths of your life and the lives of your descendants. If you think about these possible bad outcomes, what differential privacy promises you is that the probability of these bad outcomes is going to be almost exactly the same, regardless of whether you contribute your data to the computation. So it's a promise that says, basically, maybe bad things will happen as a result of us doing this study, but those bad things are going to happen regardless of whether or not you give us your data. Okay? So you could think of this as, and you could formalize this as giving some more strategic reason why people might actually participate in the computation. So since we'll mention it just in passing later on, I'll also mention, so far we've talked about sort of pure differential privacy, where we've just allowed a small multiplicative factor in the change in probability mass when we move between neighboring databases. We also have this relaxation of approximate differential privacy, where we also allow ourselves an additive delta slack. And this is really a different notion of privacy. It's a meaningful relaxation, and one way that I can highlight that is to point out that when we were just in the pure notion where we had multiplicative changes, we had no ability to move between a zero probability event and a non-zero probability event. So we couldn't have some outcome never occur under certain inputs, but occur under other inputs. That was not possible when we only allowed ourselves these multiplicative changes. But now with this delta, it is possible. So now it is possible, although unlikely, to have a smoking gun. And so it's a different and less protective notion of privacy, but it's also what gets used in practice and widely in the literature at this point for a number of reasons of convenience. So I want to highlight just a couple of properties of the privacy notion that are going to be really important for us. And the first of these is post-processing. And I'm not going to present it formally, but I want to tell you what it means. So post-processing is the property that if you do something that's differentially private, then any subsequent computations that you do on that outcome of that differentially private computation, they can't degrade the privacy guarantee at all. Once you've done something that's differentially private, an adversary can look at it and think about the outcome as hard as they want to for as long as they want to, and you still have the same privacy guarantees. And the other property of differentially private computation that I want to highlight is composition. And what composition says is that if you do multiple computations that each enjoy a guarantee of differential privacy, then intuitively the epsilons and the deltas of those guarantees add up. And this is really fundamental, and I think is what has made this notion of privacy so flexible and so powerful, is because it allows you to develop simple privacy-preserving building blocks and then to assemble more complex algorithms like you're building with Legos. And you don't have to then subsequently do incredibly sophisticated new privacy analyses. You simply add up the privacy analyses you've already done on the simple building blocks. So composition is really crucial. I'm presenting it very informally, but this composition guarantee actually holds even if your subsequent computations are chosen as a function of the results of previous computations, which ends up being quite powerful. And there's a more subtle analysis that gives even stronger guarantees than simply adding up the epsilons and deltas. So instead of, if you do k computations that enjoy epsilon differential privacy, instead of getting a k epsilon, you actually get something that looks like a square root of k epsilon. So these are the two properties of the privacy notion that are going to be important for us. And then I just want to give you one more thing before we get back to our problem, which is the simplest privacy preserving algorithm that we have is if you have a numeric computation and you want to make it differentially private, what you can do is you can add noise that takes a particular form and magnitude, and we call this the Laplace mechanism. That's all I want you to know about this, is basically there's a form of noise addition for numeric computations that will preserve differential privacy for you. And that this is one of those key building blocks. We really, as a community, only have a handful of these little Legos that we repeatedly use in developing our algorithms, and this is one of them that gets used in almost every algorithm. So, okay, so we have now a notion of privacy, and I've told you, although I don't have the time to sort of convince you by demonstration, that we have a really rich toolkit of algorithms. So you take some computation that you like to do on data, and we can tell you what's the harm to you in terms of your accuracy in imposing a particular epsilon or epsilon delta differential privacy guarantee on that computation. So let's step back a little bit and think about what do people really do with sensitive data. So again, we have all of these stories of companies who are using private data. And I'd argue a lot of what's happening here is learning. Companies want to learn to predict what you'll type. They want to learn to predict what ads you'll click on. They want to learn to predict what you'll buy. Over and over and over again, we're basically trying to develop rules that take in a limited amount of information about an individual's behavior and map that to some predictions about what they're going to do in the future that are usually going to let us make some money off of that person. And the way we do that is by looking sort of collectively at human behavior and coming up with some general rules. And so this is really one of the fundamental tasks on private data, is learning. And for us, we'll focus on sort of a particular type of learning known as empirical risk minimization, probably familiar to most of you, but just in case not. Basically, the idea here is that there are data points, they have true labels, and there's some underlying distribution over labeled data points. The learner has access to some training set of such labeled data points. And what the learner is going to do is going to try to pick a hypothesis, which is just a function that maps from data to labels, from among some given set of hypotheses in order to minimize mistakes on the training set. And maybe intuitively, it's obvious why you might want to do that. You only have the training data, so sort of what else are you going to do other than empirical risk minimization? But also empirical risk minimization, meaning finding the best hypothesis on the data that you actually have, in many situations has nice consequences for the underlying distribution as well. Okay? So this is sort of what I want you to know about empirical risk minimization. And so now there's been a lot of work on taking existing empirical risk minimizers and converting them to be differentially private and understanding what's the impact. So basically, if you want to do privacy preserving learning, intuitively at some point you're going to have to inject some noise or some uncertainty into the algorithm. And the question is basically where? Where are you going to sort of fuzz the behavior of the algorithm? And basically people have done it everywhere you might think of doing it. They've done it at the level of perturb the data and then run your algorithm as usual. They've done it at the level of perturb the objective of your algorithm and then optimize with regards to this alternate objective. They've done it in regards to compute as usual and then perturb the output of your algorithm. And then in addition, there have been sort of approaches that do sampling that's sort of weighted in a way that behaves according to a privacy constraint, and also injecting noise as you go along in the algorithm, in a gradient descent kind of algorithm. So basically, people have tried injecting noise for privacy in all the different places you could do it, and there are various guarantees that you can get for differentially private empirical risk minimization. And so these are all algorithms where you come and you say, I have a privacy constraint, an epsilon or an epsilon and a delta, and these algorithms will satisfy that constraint, and they'll do hopefully about as well as we can in terms of accuracy. And so if what you really have is an accuracy constraint and you want to optimize privacy, given the accuracy constraint, naturally one thing you could do is you could just take one of these theorems and one of these algorithms and you could flip the theorem. What do I mean by that? I mean, so take an existing utility theorem for a private ERM algorithm and solve for the smallest epsilon that's consistent with whatever your accuracy requirement is. And then go and run with that epsilon. Now, you can do this. This is theoretically sound. It's also incredibly bad. So why is this incredibly bad? Because basically, these utility theorems are worst case. And basically, you're going to go and you're going to introduce way more noise than you really needed to add. And we'll see how much more in a little bit. And some of that is because nobody really ever bothers to get the constants right, and all of a sudden you really care. And some of that's because you may be in a situation that somehow wasn't fully modeled when somebody went and developed a sort of general purpose algorithm. You may be in a situation where it's possible to achieve a very nice privacy utility trade-off. And so going and using sort of a general purpose trade-off to guide the amount of noise that you introduce is going to lead you sort of far astray. So, but this is the only theoretically sound approach to doing sort of accuracy-constrained, privacy-preserving computation that we knew of going into this work. But it seemed very natural to ask the question, can we do better? If accuracy is the first constraint, what can we do? And it feels like what you would want to do is this. What you'd like to do is try a bunch of values of epsilon. Try adding this much noise, try adding that much noise, try adding some other amount of noise, until you find one that satisfies your accuracy constraint. And then say, ha ha, I'm going with that. But there are a bunch of problems with this approach. So that search that you just did in the epsilon space is a data-dependent search. And so you need to pay for privacy, essentially, all along the way. And so you've actually hurt sort of in the traditional accounting for privacy, you've actually hurt the privacy of the individuals in the database, not just sort of in the amount of your final computation, but you've actually hurt them every time you tried an epsilon. And then there's this also sort of more subtle issue, which is if you take this approach of trying a bunch of epsilons, it's not clear how you would then state a privacy guarantee for your algorithm. Because I've just given you an algorithm and sort of try a bunch of epsilons until one satisfies the accuracy constraint. Maybe your search won't terminate, or maybe it'll terminate, but you don't know when in advance. And so the privacy parameter, the privacy guarantee that you give in the end is actually a function of your data. And basically that doesn't fit with the semantics of the privacy guarantee that we have at hand. We don't have a way to talk about privacy guarantees where the guarantee that you achieve is a function of the data. So that's the first issue that we had to tackle here. And now I'm going to give you sort of, given the time, a sort of high-level view of how we deal with each of these parts of the problem and how that helps us. So basically, we're going to do a principled version of this epsilon search idea. And what we give is a meta method that does this search that you can then go and apply to various types of private ERM algorithms. And I'll sort of make that a bit more specific in a moment. But basically, at a high level, we're going to start by computing a very private hypothesis. So we're going to be very, very conservative. And what we're going to do is we're going to, in our epsilon search, we're going to repeatedly degrade the privacy guarantee by doubling is how we're going to search until the accuracy guarantee is met. And we're going to do this doubling in a way that makes us not pay extra for each new computation. So basically what we're going to do is we're going to use correlated noise that's carefully correlated across the rounds so that you can subtract noise from previous iterations in order to get the next iteration. And this allows us, in the end, to pay only for the final sort of least private computation that we settle on. So we start with something very private, we make it less and less and less and less private, and eventually we say, OK, that's as well as we can do in terms of our accuracy constraint. And because of the correlated noise, we're able to just pay for that last round. And then what we need to develop next is a new algorithm that lets us minimize the privacy costs of doing this checking of whether we're done. So every time we try a new level of privacy, a new epsilon, we have to ask ourselves, did that satisfy our accuracy constraint? And if not, OK, we finished. And so we need a new approach to allowing us to pay as little as possible in doing this sort of repeated checking. And then in the end, what we're able to get is something that pays only the privacy cost of the final hypothesis plus some additional overhead for checking. As I mentioned, we're going to need sort of a new notion of privacy, in which we call ex post privacy. These things that we're doing here don't satisfy a priori epsilon differential privacy for any fixed epsilon. But intuitively, if our algorithm terminates at some point, it seems like it satisfies some notion of privacy loss. And that's what we make formal, is that basically we talk about now privacy guarantees that are parameterized by the outcome you select. And we look actually, sort of given the outcome of the algorithm, what is the ratio of probability masses under neighboring databases on that outcome. And we talk about ex post privacy loss as being something that where you have a function that maps from outcomes to losses and says that you're guaranteed to sort of obey the constraints imposed by that function. So this is a way to now talk about privacy guarantees when you don't know a priori when you're going to stop and what the privacy is going to look like. And sort of the key idea of the correlated noise comes from this paper of Kufganianis of this past year, where basically think of it as you're generating noise according to a continuous random walk that starts at the private data, and it maintains the property that the marginal distribution at each point in time is Laplace noise centered at the true value of the data, and you're increasing the variance over time. Now, if you roll back such a random walk, and sort of reverse that process, then you have exactly what we need. Basically, your more private points can be derived from your less private ones, and therefore you can just pay for your sort of least private computation. The key ideas behind this checking algorithm, where we basically are repeatedly trying to decide if we've gotten where we need to go, is that there's an existing algorithm that basically takes a threshold and an adaptively chosen potentially sequence of queries and tells you the first time the response to one of your queries exceeds a threshold. The reason we can't use that technology is because for us, the queries that we're issuing actually depend on the data. And naively, in order to use this existing algorithm, we need to publish the queries in advance and pay for them all. So we need to come up with a new way of analyzing a closely related algorithm that sort of lets us iteratively generate queries and only pay as we go. And so we come up with this sort of general framework that lets us take any ERM technique that you could describe as a post-processing of a Laplace mechanism. Or again, a Laplace mechanism is just sort of adding this noise. And so what falls in this category? There are various output perturbation algorithms that fall in this category where you're adding Laplace noise to the result of your learner. And there's also this covariance perturbation idea where you're perturbing the covariance matrix of the data. Basically, you're messing with the data before you even do the computation, before you go and learn. And then you optimize using this noisy data. So both of these types of approaches are amenable to our sort of general meta-algorithm of doing accuracy-constrained private learning. And basically, given the time, I'll just tell you the bottom line is that this approach that lets us search in the epsilon space is a big win. It's just incredibly better than just simply inverting the theory curve. So doing that I have a theorem that tells me about trade-offs between privacy and utility. Let me impose my accuracy constraint and solve for the epsilon. And it also significantly improves on a more naive sort of epsilon search approach where you pay for all the epsilons that you try. And I'll just show you, maybe given the time, I'll just look at one curve together. So this is a comparison with inverting the theory curve. And this is a setting of ridge regression. I think in this case what we were doing is trying to predict viral tweets. And the blue line is us. The red and yellow lines are two different theory curves for two different algorithms. And you don't know how to interpret this, right? We're doing better, but how much better are we doing? The thing that I want to remind you of is here on the y-axis, we have epsilons. But if you want to talk about how bad the privacy loss is, you should actually be talking about e to the epsilon. That's the multiplicative. So think exponential in this axis is the improvement that we're getting. So we're seeing things even on curves where our sort of benefit is less impressive when we're comparing with the sort of naive doubling method. We're seeing an improvement of orders of magnitude in terms of the privacy loss that we incur. So empirically, there's something nice here. And along the way, I think there's some interesting little theory challenges that we had to come across. But there's some things we still don't understand. One thing that actually really surprised us when we went to do the experiments on this data is that the privacy loss that we incurred from doing this testing actually ended up empirically being significantly larger than the privacy loss we were experiencing from generating hypotheses. Some of this is probably, there's a loose analysis that forced us to use, to do things in a way that was probably non-optimal. But I don't really understand sort of what's necessary here and what's achievable in this space yet. And the other thing that was a little bit nettlesome along the way is I told you that a lot of the real world uses epsilon delta differential privacy. Everything I just told you about actually only applies to epsilon differential privacy. And there's a subtlety in the analysis of this interactive above threshold, this algorithm that's sort of checking whether or not our attempt at an epsilon was good enough, that we can't figure out how to handle with this relaxed notion of differential privacy. It seems that the theorem that we proved for epsilon differential privacy is simply not true for epsilon delta, but there may be some other theorem that is true. Anyway, I'm out of time. I'll stop here. Thanks, guys.
Questions? Just to be sure, the trivial doubling techniques, you cannot improve more than a factor of 2 on that, yeah? Because
you can, because so the trivial doubling techniques, you're going to get, because there are a couple points where you can lose a factor of 2. As far as so there's a factor of 8. There's a factor of 8, but then we're talking about exponentials. So a factor of 8.
The epsilon is approximately epsilon.
Pardon?
E to the epsilon approximately 1 plus epsilon.
Yeah, so we're talking about sort of privacy losses that are, we talk about sort of e to the epsilon and privacy loss. So if your epsilon is a factor of 8 off, you can still really care about it. But that's right. Yeah. Other questions?
Okay, thank you.
Thanks, guys.